Consider the following 2019 AMC 12B problem number 25, and here is a view of this geometry problem. We are given a convex quadrilateral with side lengths BC equals 2 and CD equals 6. We would like to mark these the centroids of these three triangles, and apparently they form an equilateral triangle, and as a result our inquiry is to figure out the area of this quadrilateral ABCD. Let's go ahead and draw this quadrilateral. Okay, so maybe let's just do a little bit. How about that? Yep, that's good. So A, B, C, D. We know this length is a 2, this length is a 6. We need the centroids of the following triangles. So let me first go ahead and draw the triangles by just first drawing the diagonals. And now time to identify those centroids. Well, obviously I need to mark the midpoint of AC, so say somewhere here. So as a result, if I go ahead and draw the median, something like this, and maybe the median here, there you go. So yeah, it would be pretty much here. So that's the centroid of triangle ABC, call it G1. And in a similar way, I can find the centroid of triangle BCD. We might as well just draw the medians as usual. So maybe one here, oops, something like this. So let me just go ahead and do something even faster. Let me just try to eyeball a third of the distance between this midpoint. Okay, so something like that. All right, and finally, we just go ahead and draw the last median, this one, for triangle ACD, that one. Oh, so the previous one, we should have labeled it as probably G2, and the last one would be so roughly I'm eyeballing, right, so I'm trisecting that segment, so yeah, that should be here. So we have a G3 here. The claim, as I suggested earlier, is that G1, G2, G3 is an equilateral triangle, so something like this, like that, like that. So we have this equilateral triangle here. Then we want to maximize actually the area of quadrilateral ABCD. Okay, so I need some sort of a crux move, and upon inspecting, and especially the idea that the centroids trisect the medians, I think it's clear that G1, G3 is simply parallel to BD. I think it's fair and easy to say that. So let me write that down here. G1, G3 is parallel to BD. And the reason being, if you call this midpoint here as M, it's clear that MG1, G3, let's write it down, because triangle MG1, G3 is simply similar to triangle MBD, because of side ratios. So MG1 to MB is 1/3, and MG3 to MD is 1/3. So as a result, you get the desired relationship. So far we know that this segment here is parallel to that one. That's pretty neat. But then we can use again homotety, and let's see if you guys can figure this. But so for instance, if you notice, if you label this point here as N, this time if you focus on the homotety centered at N, taking G1, G2 to AD, right? I think it's clear again that those two would be parallel. Why? Because NG1 to NA is 1/3, and G2 to ND is 1/3. As a result, those two triangles are similar. So we have G1, G2 is parallel to AD, simply because triangle NG1, G2 is similar to triangle NAD. So that's the second parallel lines. Okay, so those two lines are also parallel. And lastly, we can do one more argument. Focus on G2, G3. And let me draw one additional line that can probably help you guys. If I did draw MN, notice that MN is the midline of triangle ABC. And now it's clear that G2, G3 is parallel to MN simply because of homotety center that D creates two similar triangles D, G2, G3 and D and M. As a result, G2, G3 is parallel to MN, but MN is the midline of triangle ABC. As a result, MN would be parallel to AB as well. So I'll leave the details to you, but that's pretty much the idea. So we have G2, G3 parallel to MN, simply because dilation at this point, and triangle DG2, G3 and DM and M being similar. And then NM itself is the midline of triangle ABC. As a result, it's parallel to AB. Perfect. So now we know that G2, G3 is parallel to AB. Do you guys agree now that the three sides of this equilateral triangle in the middle are parallel to the three sides of triangle ABD? As such, those two triangles must be similar. So triangle G1, G2, G3, G1, G2, G3 is similar to triangle D, G1, G2, DAB, simply because angle, similarity. But because this triangle itself, G1, G2, G3 was an equilateral triangle, that should imply that this triangle is also equilateral triangle. So that was the crux move of this problem, noticing that ABD is an equilateral triangle. Now we can go back to our question and finish it, because the question is an optimization question where we try to find the maximal area of quadrilateral ABCD. We can indeed split it into two pieces. ABCD is equal to ABD, area of ABD, plus area of BCD. Well, ABD is an equilateral triangle. We just established it just a minute ago. So therefore, something that would that can tell us about the side length of this equilateral triangle ABD, if we can relate it to the somehow to triangle BCD, then we would be done. And it's, I think, obvious how to do it. So all you do is, if you mark this angle here as theta, then we can go ahead and apply law of cosine on triangle BCD. That would give us a BD square equals 6 square plus 2 square, which is 40, minus 2 times 2 times 6, which is 24 cosine of theta. And now once we establish BD square, it's clear how the area of triangle ABD would simply be side length square root 3 over 4, but side length square is this thing that we just calculated, BD square. So therefore it is just root 3 over 4 times 40 minus 24 cosine of angle theta, and that's simply equal to, after dividing by 4, we would get 10 root 3 minus 6, I think it's 6 root 3 cosine of theta. Alright, so all we need is now the area of BCD, but that's also pretty easy, very straightforward actually. So the area of BCD, you can use the sine area formulation, 1/2 6 times 2 times sine of angle theta, but the 2's cancel here, so we have 6 sine theta, right? So let's just write that down one more time. And now we can go ahead and add these two quantities, and that's the sum that we want to optimize, and our choice variable is theta basically. So maximize by choosing theta, 10 root 3 plus 6 sine of theta minus 6 root 3 cosine of angle theta. That's a theta. Okay, some space here. And now to optimize it, well, obviously this is fixed, so it doesn't really matter. So all we should do is to focus on the second part, and I think it's clear that we can manipulate this expression so that we can get a summation of the sine formula. So this thing is the same as 10 root 3. Factoring out the 12, we would be left with 1/2 sine of theta minus root 3 over 2 cosine of angle theta. Well, I can replace the 1/2 with cosine of 60 degrees and replace this one with sine of 60 degrees. So that just reduces to 10 root 3 plus 12. And let's see if that rings any bell. Huh? So let me write it the other way around. So it's sine theta times cosine of 60 degrees minus cosine of theta and times sine of 60 degrees. But then this is just the sine summation formula, sine of a difference, I should say, because there's a minus here, theta minus 60 degrees. And that's it. So that's exactly the expression that we want to maximize, but that will achieve a maximum when so sine is always less than or equal to 1, suggesting that this expression can never exceed 10 root 3 plus 12 plus just 12. And when would that happen? So to find the maximum possible area, so we just did it actually. So that would be the maximum possible area, and I hope this is one of the answer choices. Yeah, I think it is. So 12 plus 10 root 3. And if you are curious for which value of theta we can do that, obviously sine would be exactly equal to 1 if the angle is 90 degrees. So therefore that would imply where theta minus 60 is 90. So therefore theta is 150 degree angle. So this angle here is a 150 degree angle, and then the area of this shape would be maximized, and we're done with this really nice AMC 12B problem number 25. Hope to see you guys in our next lecture.